Aloha, everyone. My name is Audrey Lynn, and this is my partner Chisato Kay. We are so grateful that you all took valuable time out of your day to listen to our presentation. Today, we are going to present our Kay Fellowship project, modeling the impact of urban form in Honolulu on carbon emissions in the household sector. Our mentors are Dr. Paul Bernstein, an economic policy expert at the University of Hawaii Economic Research Organization, or UHERO, and Dr. McKenna Kaufman, who is also a researcher at UHERO, a professor of urban planning, and the UH Director for Sustainability. Before we begin, we want to thank Papa Jack for generously granting us this incredible opportunity to meaningfully investigate these important issues.
So in the 21st century, many researchers view the climate crisis as the single greatest threat to mankind. Amidst this inconceivable urgency, the energy policies of the United States, the second largest global emitter of carbon dioxide emissions, holds tremendous weight. In fact, 41% of American emissions are caused by transportation, commercial, and residential emissions. A growing body of literature points to urban form and development as a primary determinant for these types of emissions. For example, researchers in Texas found that low-density suburban housing, characterized by detached single-family homes, emitted 320% more embodied energy than high-density housing, characterized by higher-density apartments and duplexes and multiplex housing. In most American cities, it's illegal to build anything other than detached single-family homes, and this applies for over 75% of most residential land in most American cities. And this in part explains why the United States is one of the most carbon-intensive nations and why it's imperative to evaluate what systemic urban reforms can be enacted, steering energy demand in the household sector to a more sustainable direction. So this study, coupled with the intense need for local, tailored, and accessible research, leads us to our research question. In Honolulu, is there a quantitative relationship between household energy consumption and regulated housing density based on residential zoning designations? So there are two major categories of residential zoning. The first being low density zoning, which is restricted to detached single family homes with minimum parking and lot size requirements, strict height restrictions, really sprawled out, like we see here, where there's lots of land and resources being used for a very little amount of housing. And it also means single use zoning, meaning the zone is only reserved for housing and you can't mix in things like grocery stores, restaurants, libraries, cafes, etc. And in Hawaii, these take the form of R zones, where each number next to the R stands for the minimum lot size requirements and square footage. So I'm just going to show a couple more photos. These are all Honolulu, by the way, around Kapolei. And they really make up the vast majority of zoning, not just in Hawaii, but in the United States. So the second category of zoning is high density zoning, which zoning that restricts spreading out and instead allows for building up. And it's typically more flexible in terms of parking and lot size requirements. High density zones also tend to be more mixed use, meaning you can build housing, schools, offices, restaurants, libraries, all that kind of stuff, all in the same zone. And in Honolulu, these are the high density mixed use zones, like we see over here. And like the rest of America, they're very rare. So we hypothesize that in Honolulu, lower greenhouse gas emissions will be found in higher density zones. We expect the greenhouse gas emissions will be inversely correlated with levels of density and housing regulations.
So our methodology had three major steps: data collection, spatial analysis using geoprocessing tools on ArcGIS, and statistical testing. But what's on screen is a major oversimplification. In reality, the process ended up being neither linear nor chronological. Instead, there was a lot of backtracking and redoing steps to refine our data, rerunning different scenarios, and pursuing various steps simultaneously. So our data was split up into two major categories: private vehicle emissions from commuting to work, and emissions and household energy expenditures. Because there is no raw recorded emissions data on this granular of a scale, this process involved us sourcing existing census data as a proxy for household emissions. So, for example, for vehicle emissions, we took the census data for average commute time frames and average vehicle speed from the existing census databases, in this case, the 2020 5-year American Community Survey. Furthermore, we utilized fuel efficiency data from the Toyota Corolla, a common car in Honolulu. And we also derived the EPA's greenhouse gas factor for carbon emissions emitted by motor vehicles. And in the end, that would give us the approximate measure of emissions per census tract. One of the caveats here, though, is that census tract data only describes the time spent commuting to work, and there's no existing data granular enough to observe transportation for leisure purposes. So all that time we spend driving to Costco on a Saturday is unfortunately not accounted for. So this next formula does the same, but with household electricity expenditures. We take the average electricity expenditure per tract from the LEAD database, then the average electricity rates from HECO during this time frame, which is again the year 2020. Again, we take the E-grid factor for CO2 kilowatt per hour to ultimately get our total CO2 emissions in kilograms. So another caveat that you probably caught was that we are using the year 2020 as the time frame for our research, which is not an ideal year because of the big behavioral changes during the pandemic. So again, this combined with the vehicle emissions are likely underestimating how much households are actually emitting. Then using geospatial analysis tools on ArcGIS, a geographic information system, we joined the emissions data with each of the census tract parcels and then tabulated the spatial intersections or overlay between these census tracts and the Honolulu zoning designations. This way, we can look at every census tract and see how many zoning parcels are overlapping in the tract and how much. To quantify density, we developed an ordinal ranking system of residential zoning designations. These ordinal rankings of zoning designations were based on square footage requirements or the floor area ratio listed in the Honolulu Land Ordinance. The least dense residential zoning designation, Country District, was allotted the lowest ordinal ranking of 1, while the most dense residential zoning designations were allotted the highest ordinal ranking of 12. Many tracts comprised of multiple residential zones, so if a tract is too heterogeneous, it cannot be included in the dataset. As a result, a cutoff method was devised to determine whether or not a census tract was homogeneous enough to be included in the final set of data for analysis. And to boil it down, the cutoff works by assigning a census tract composed of more than 75% to that zone.
Okay, so now we want to kind of go over our results. So the two graphs here show original zoning designations on the x-axis and greenhouse gas emissions on the y-axis. So after running a linear regression, we found a negative correlation between zoning density and greenhouse gas emissions. The leftmost graph shows household emissions with the R-squared value of 0.401, and the rightmost graph shows transportation emissions or commute emissions with an R-squared value of 0.4. So this graph shows the linear regression run for the total greenhouse gas emissions versus zoning designations. And this is an R-squared value of around 0.435. And the range of the annual greenhouse gas emissions per household goes from 2,700 kilograms to 9,393 kilograms. To put that to scale, a flight to California is responsible for around 450 kilograms of greenhouse gas emissions.
So another measure of density is population density. We obtain population density data from the census by dividing total population per census tract by square mile. The correlation coefficient is 0.296, a smaller but still significant correlation. With a high degree of confidence, we can say that there is a strong correlation between both greenhouse gas emissions and zoning designations and greenhouse gas emissions and population density.
We want to acknowledge that while the study is a good start, there's still a lot more to be done. Future research should include increased sensitivity analyses in which values such as increased fuel efficiencies or newer vehicle models can be tested against the same equations to see how much an individual change, behavior, or local policy can impact these results. And there should also be more research done on how much these changes in emissions can vary across different socioeconomic groups and household sizes. And it's important to acknowledge in general that, with these studies based on like socioeconomic research, there's a lot of assumptions and caveats that we have to reconcile with. So local, accessible, and tailored research is the key to creating efficient policy that's affecting systemic mitigation to the climate crisis. We're excited that our project is novel in that aspect. So in our current landscape, these results affirm that the domination of detached single-family zoning with minimum land and parking requirements has left little room for sustainable development. Government policy is necessary to make a difference, like a lot of other issues. For example, in 2021, California effectively put an end to exclusive single-family zoning by allowing owners to convert their homes to duplexes, regardless of local zoning. Similarly, we recommend that in Hawaii, legislators deregulate height restrictions, floor area ratios, minimum parking and lot size requirements, and end single-family zoning like they did in California. In the meanwhile, the climate crisis is only growing worse, and the urgency for government action is increasingly evident.
And we wanted to acknowledge that our results support our initial hypothesis. And in terms of novelty, our study is the first for Honolulu in terms of its variables and granularity on a census tract level. So in my reflection, I wanted to stress the importance of tapping into resources. This summer, I truly learned the importance of a cold email, and I want to thank Mr. Kwok from Hawaiian Electric and the creators of the Lead Tool team for answering emails from two small high schoolers with big questions. To future K Fellows, be curious, be active in your search for data, and don't be afraid to ask questions.
Yeah, in my reflection, I guess I want to emphasize to reconcile with imperfections rather than getting stuck on the imperfections, and being able to, again, reconcile with, all the caveats and assumptions that you're going to have to make, because in the end, you have to always look at the bigger picture. Oh, and also, I want to thank Stephen from IT for lending me a laptop over the summer. We really couldn't have done it without the laptop, so thank you.
Yeah, so Chisato and I want to thank you all for coming to our talk. But we also want to say mahalo to Dr. Chan for her incredible guidance. Obviously to Stephen from IT, and to Renee and Cami for helping us with GIS. And to our mentors, Paul and McKenna, for their indispensable help and tremendous time they selflessly gave to this project. We couldn't have done it without your support. So thank you guys. And we wanted to open the floor to any questions that you all might have. Thank you.